All right, here is the recording for today's class where we'll be talking about this concept of goodness of fit. And this is somewhat of an abstract concept of how does the expected value compare to what we're seeing. And this has been a concept that we've started to explore through the hypothesis testing framework and thinking how similar are these two different groups? And if they're not similar, by what degree are they significantly different? So this module will be talking about the F distribution, which we got a little taste for in the last class when we were analyzing the variance. This will now look into comparing two different variances of two different groups. And then we will talk about these different tests from the chi-square family of distributions, where we're looking to see this goodness of fit test. We're going to test if the data is independent from each other and test for homogeneity. And a lot of these things we'll be talking about how it relates to how we've continued to assume that our data is normally distributed and there's not necessarily the skewness that might prevent us from using all of our assumptions of normal distributions and the z-score and using all of the things we've built and established our foundation on. These tests we will talk about today will be used to explore in the future, is this a valid assumption that you can make statistically? So this class will essentially bring us to a conclusion for the hypothesis testing and get us into other applications of tests for our assumptions that we've been making throughout this semester. So let's get started. And this whole concept of actual versus expected will continue to be a theme. So this whole time when we've been using statistics is really to create some type of inference about a population that we don't really have any understanding about to like a concrete degree. So we're using all this inferential statistics to better understand a population. And so when we're getting into this F distribution, this is now starting to compare the variance between two certain groups. So this relates back to this last module we recorded last week when we were looking into the growth versus value portfolio returns and seeing like how much variance existed between the two groups. So this might also relate back to control of quality and seeing how much variance exists between different suppliers, different groups. In this case, this is looking to see if you were in charge of manufacturing and you had different suppliers you could choose from, you could use a test like this to actually inform the decision between two different options to know, does this supplier have more, variance in how they manufacture something in a statistically significant way to make sure that, hey, I should go with this supplier over this one. And this is my rationale as to why. And we can actually measure how much variance exists between two different groups and use statistics to inform what that ratio of difference actually is between two groups within a population. And so in this case, we're using this ratio of variance of the group of 1 over variance group of 2, and seeing if this proportion is significant enough to say there is a difference between the variance of two different groups. So we'll be using a similar type of null hypothesis testing framework. And I will now just talk about the different inputs that are required for when we run these tests. Again, one of our key assumptions is that this data is drawn from a normal population. And the new elements here to consider are having 2 degrees of freedom, one for the numerator and one for the denominator, where the last time when we had this chi distribution, we only had 1 degree of freedom that we needed to worry about. But in this case, now we're comparing this proportion. So we need to define the degrees of freedom for one group compared to the degrees of freedom for another group. So we're kind of shifting 2 separate groups and needing to account for this lack of freedom when you're calculating an exhaustive amount of values. Similar with the hats, when we were first introducing this degrees of freedom, we're pretty much looking into what is the variance in this one group, and we want to calculate that. and what is the variance of this other group, and need to calculate that. And then we take this proportion between them and we see, is this proportion very different? So if you took 100 divided by 100, the proportion would be 1. So you wouldn't see any difference. But if you have 100 divided by 50, you would have this higher or like a lower proportion to know that these two groups are different. So we're using these aspects of just division to see how different is one group from the other. And we need 2 separate degrees of freedom for the top and the bottom, because these are 2 separate elements. And then we're just finding this proportion between them. So that was just to explain why we have degrees of freedom for the numerator and the denominator. These are essentially 2 different components, and then we're just comparing them to each other to see how much of a difference exists between these 2 different distributions. So this is the framing of how we will start to create like our test statistic and solve this type of problem. And different things to talk about too is we're looking at this probability distribution of the ratio of 2 different independent variables. So in that last example, if we were talking about, let's just say like defect rate, we would want to look at the variance of defects between supplier VB compared to a supplier DG. So those would be just 2 separate groups, and we would start to look at these different distributions of 2 independent variables. Any questions regarding what we're getting at right here? Really, the key takeaways are that we have 2 degrees of freedom to calculate for the numerator and denominator, and we're comparing these 2 different distributions and looking at the variance between them.
Can you just remind us the degrees of freedom and the significance that has on statistics?
Yes. So there's kind of 2 aspects of degrees of freedom that are important to think about. The first one is just how to use it and when to use it. And that would be if you are using the table in the back of the textbook for calculating the specific critical value, compared to if you were using it in Python. You don't necessarily need to know how to use the table, but having the table, you need to use the degrees of freedom to know which value to go for. So the significance there is just knowing when you have degrees of freedom, how to use it, using the table, and then also just as an input when you are calculating any of these things. So that's the first aspect. But the reason why it matters is because we need to use these formulas and calculations, and they assume that each value is independent from each other. And I bring it back to the hats because that was an example of if you have 7 hats for 7 days of the week, you don't necessarily get to choose which hat you're going to wear on day 7 because you only have one option left. So we remove that last day of wearing hats because you don't have this freedom to choose what hat. It's almost just assumed that whichever hat you haven't worn yet is what you're going to wear. And that gets back to just the validity of using these calculations, where you can't have this one remaining value left because it's already default whatever hasn't been calculated yet. And does that aspect make sense? It's more so like this abstract use of math that requires taking 1 degree of freedom out because of how things get calculated and added together. And I could bring one other example, perhaps just to help solidify this. Like if you're trying to calculate the average of certain values, if you have like 5, let's say the weight of 5 jelly beans and you have the average and you know what the weight is of 4 of those, you can like subtract that to get the weight of that last jelly bean. And because of this, you don't really need to calculate what that last jelly bean weight is because you have the different sides of the equation.
Okay, and you minus the 1 because the likelihood that you'll get a more accurate weight is helped by minusing the 1. Is that why we're doing that?
You subtract 1 to allow ourselves to be able to use these formulas and you subtract just 1 because it's accounting for that last jelly bean and that last day of wearing hats that you really don't need to calculate because it's the last remaining value.
Okay.
So it's really kind of almost like, if I can be somewhat, this might not like mathematically be the right way of thinking about it, but it kind of just allows us to use these formulas by like almost hacking the formula by saying, okay, we'll just remove this last one. Don't think about this last one, so that we can apply these mathematical calculations.
Okay, and the chart helps us get closer to the accurate calculation, the table.
The table gets you to that critical value of how much area under the curve.
Okay.
And so, yes, so subtracting 1 from each gets you closer to the most accurate value
Okay.
for that. But really, it's more so that we can use the table itself, and like use all of these assumptions is why you need to subtract 1.
Got it.
So really, yeah, again, just at like kind of a high level, you subtract 1 so that all of these assumptions and mathematical formulas are accurate. And me trying to explain the math behind it is using that hats and the jelly beans example. Because really it's just so that we can use these assumptions and they don't get violated by knowing what that last value would be. So if you can just kind of take that at face value of we subtract 1 so that the math is valid, so that we can get to an accurate, table value, could be a good way of just thinking about it.
Okay, thanks.
Yeah, these are great questions because we continue to see this degrees of freedom, and it's a little bit abstract of like the why, because it really is just so we can use these formulas. So we already saw this distribution in the last class, but just for a refresher, where we have this sample size that might change based off of how many observations we have. And the more observations you have, the more normal the distribution looks like. So we see here with degrees of freedom are essentially just the proxy for how many samples do you have, and samples in the numerator and the denominator now for these 2 different degrees of freedom. So in this tuple of parentheses, the first value is how many observations minus 1 or degrees of freedom are there in the numerator, and how many degrees of freedom are in the denominator. And we see this type of right skewness, so very positively skewed. And as the number of degrees of freedom become larger, we approach a normal distribution. Any questions regarding just like the shape of the distribution?
Yeah, just a quick like I guess refresher. So the different shapes on the graph indicate what exactly?
Yeah, the area under the curve. So what is this probability density function of a value? And so the curve represents, the area will equal 100%. But if you had a value, let's just look at this like orange curve, for example, and hypothetically, like you just had a value here, this would be your mean of where do the values, are they the most dispersed? This normal curve of most values are right in the middle where you have the mean. This is showing how that normal distribution that we're familiar with just gets skewed to the right. So back to, module 6, where we just started learning about continuous distributions. This is that same area under the curve that we're familiar with from the normal curve. It's just skewed because this is the F distribution. Does that help answer the question?
Yes. So basically the green one, the mean would be like, I guess, on the other side of the graph that we don't see.
Yeah, I mean, and I don't think we can get negative, so there might not be another side of the graph. This is now like bringing that normal distribution into other practical senses. So yes, if you only had, 3 observations and 9 observations in one example, we can't assume like the symmetry to exist. So we account for that lack of symmetry because of the lack of sample size. And getting back even with Mara, what you were bringing about around using the table to get an accurate understanding of what the area under the curve would look like. We can't be as accurate because we have a small sample set. So I'm sure it probably almost penalizes the value more than it would when you have this degrees of freedom of a larger sample size, where you kind of do have more of a symmetry to work with, where in this case, there's going to just be less kind of accuracy or just more room for error because of the smaller sample size. So yes, to answer the question, like the mean would be somewhere around here, but the table would account for the lack of sample size in that value. So there's kind of just more room for error, and it's a little bit less kind of reliable as a measurement compared to something with a larger sample size. And this accounts for that in this, like the pre-computed table, and just the shape of the distribution is all trying to account for how this might relate to real life.
Okay.
And that's really good to bring up again, because I don't think we can, repeat it enough, because this is really core to what the key takeaway from our class is like how to work with area under the curve and apply it back to our inferential statistics. And now we're getting into kind of more of the nuances of how things might work in the real world when we would apply these types of approaches. So talking more how we would use this. Again, it's been very similar of having like area under the curve, and now compared to the last few classes as we gotten into hypothesis testing. This will be very similar to this last module of the chi-square test, where depending on if we're trying to say, is the variance greater than or less than a certain value, we would have that to be a like a one-tailed test. If we're trying to say like the variance between this is less than a certain value, or if we're just trying to say like the variance is equal or not equal, we would have this two-tailed test. And so really the difference here is because we're looking into such a skewed distribution, we have the different degrees of freedom in the numerator and the denominator to help derive these given values of the distribution. But a lot of the concepts have been very similar as before. The area under the curve will all equal to 1. And we use this to understand, given a certain location on the distribution, what's the probability of seeing a value at least as extreme as that, because this is all representing the distribution of values. So all of that is just visualized on the right. For example, if you had a distribution with the F distribution and you had this type of degrees of freedom and it's less than 0.24, we would know that that is on the left-hand tail of this distribution, and it covers about just this little tail, which is kind of interesting then to look on the right side tail, where a value would have, this is 3.58 standard deviations from the mean, which is here, compared to this value, which is just 0.24 standard deviations below the mean here. But these would still be considered tails. So we work in this in the same way as we have before. It's just now understanding, hey, this is a different distribution curve, and we work with it in a slightly different way because we have these two different degrees of freedom. And so bringing that back to how we actually calculate this, it's going to be similar with this confidence intervals. If you wanted to calculate it by hand, we would use the table in the back of the textbook, but we can also in Python use the same SciPy package for the PPF value itself. So we can walk through that now. And then as we get into other parts of this module, we'll talk more about how we frame this in hypothesis testing land. So for now, let me just show you how we would go from a question like this, like what we just saw, to get to the actual value. So a lot of the homework questions will look somewhat similar to this, where you have just like the basic inputs, and it's to find what is the critical value of that. And this type of critical value will then be used for hypothesis testing down the line. So let me just clear our output so we don't see that ahead of time. And today we'll be jumping a little bit back and forth between the PowerPoint and using the demo itself. So these are all packages we've seen before. There's nothing new that's being introduced. This is now just talking about the F distribution. And there's lots of different ways to denote degrees of freedom. You know, we've seen DF before. And so now I will just use DFN to demarcate the numerator degrees of freedom and D for the denominator. And I am defining variables to then use later on. So in this case, we are just trying to find what's the distribution from the F distribution with these degrees of freedom that's greater than this value of X, so of 0.025. So we're trying to find this upper tail probability. So bringing us back to what we just saw, you know, this would be something like this, where we're trying to find what's the value, or like how many standard deviations away from the mean would leave us with area under the curve equal to, in this case, this is 0.05, and just this demo is looking for 0.025. So we could do this for 0.05 if we wanted to just see how that would compare from what we just saw, you know, but in this case, we'll get to that point in here. So let me go back to what it looks like. So I will just define those as our, what's the probability that we're looking to calculate for. These are the number of degrees of freedom in the numerator and the denominator. And to use now, this is different. As we've seen before, we usually have the dot norm or dot chi. We've seen lots now, and dot t. So now we're using dot f for the F distribution. And this is how you would get that critical value. So in this case, we have to subtract from 1 because we're looking for anything greater than that value. And here, when you don't need to have it greater than, you don't need to subtract it from 1. So here would be how many standard deviations away from the mean to get to the area 0.025 under the curve. And so here, this is when we use those inputs. And if you were to be using the table, it would be very straightforward compared to last class. You just have the two different values to be looking at for the degrees of freedom. So this would get us to what that critical value is. And if we wanted to then get that back to area under the curve up into that point, we can, you know, kind of go back and forth using this cumulative density function based off this critical value. So this is pretty much saying how much area under the curve is being accounted for up until this value. So this is just showing the two sides of the coin and how this all adds up to 1, and how we, you know, use this probability density function to slice and dice to know how far away from the mean does a value need to fall in order for it to be, you know, something significant.
Can I just ask you a question about the curve?
Yes.
When we're saying that it's 0.975 away from the curve, are we talking about the midpoint of a normal distribution curve?
This is a good question, and definitely let's clarify this, because this is how much of the pie is being filled up. So even let me just draw this, because let's like think back to that first class when we had the area under the curve, the cumulative density function too. So that 0.975 is just saying we're filling up all of this area under the curve and just leaving this 0.025. So what you were saying of like, how far is it from the mean? This is actually saying something different. This is like the cumulative density function of like how many variable, like how many outcomes from this random variable, the majority of them will fall below whatever value is here. And only 0.025 will be in this area that's not shaded in.
Okay, and as far as inferences that we can make about data, given that critical value information, what are some insights that we could make about the data with that information?
Yeah, exactly. And so the insight that really comes from the hypothesis testing framework. And that's when we can say, hey, we saw a value that fell over here. And because it is, you know, in this case, if we saw a value that fell over here or over here, we could say, bringing this back just to what we're learning today, if we saw the proportion of variance significantly vary from the mean, so let's just say like this is what we would expect to see if there was no difference in variance between two different groups. And we saw, you know, kind of just due to how there is variance naturally in things, if there was no significant difference of variance between two different groups, you know, you might see a value that falls here, you might see a value that falls here, you know, nothing will exactly be at zero unless you're kind of in like an experimental setting. So this type of distribution accounts for just the natural way you might start to see a value fall. Even getting back to like that Plinko example, you won't always see it fall right in the middle. It'll vary a little bit above or below. And then the insight is really drawn if we were to see a value that falls over here, it's far enough away to what degree to say seeing a value over here is rare enough that it is so far away that there must be something significant here that we just found. Because if there wasn't any significant difference between the variance, we would see values that fall closer to this middle line here. And that's how we use this significance testing framework to say we saw a value so far away from the mean that it could be statistically significant at this threshold. So if we saw something that was all the way over here, let's say this was like 0.99 area under the curve, or like more than 3 standard deviations away from the mean, you know, to kind of just this extreme level, we could say, hey, the variance is so different between these two different groups, and we would only see a value at least as extreme as we did here. You know, 0.99, you know, 1 out of 100 times, because we have this 0.99. So the chances of us seeing this due to chance are just 1 out of 100, but we did see it. So there must be something, you know, jelly beans do cause acne, or like there must be something that we found here that is significant.
Okay. Okay. So the fact that it's so like 95, whatever the number was, it was in the 90s, the fact that it is so, there's so much that has gone before that, and there still is something of significance at that point in the chart, we need to look further there. And that's the insight.
Exactly. It's saying like, hey, this isn't just the average thing that would usually happen. There is a significant difference enough that this value would be very rare to see just due to chance.
Understood. Thanks.
Yeah, and that is like the crux of everything we're doing here with any distribution. So where we are in class right now is just taking this concept that we just walked through and applying it to different types of tests and different questions that we want to ask. But at the end of the day, this would even apply back to like finding outliers. You know, how far does the expected value fall from the average? And even just, I hope I'm not confusing by trying to tie it back to other things we've learned, But thinking back, even like, does the mean vary far enough? Getting back to like the first type of hypothesis testing we were trying to say. So it's all trying to say, how does this compare to the usual? And the usual is everything that falls closer to the mean. And is this far enough away from the usual thing that happens to say we found something significant?
I'm really glad that you discussed like what a sample insight might be about this type of data set, because it's centering me in like, at this point of research, we don't actually understand what the variables, and we're not coming to major conclusions around like our hypotheses. We're just observing sort of uncommon or common things about what is in the data that we're seeing. So
yeah, exactly.
we should be looking further here, or we've come to a conclusion, is really like, you know, the majority of what we can actually come to conclusion about, given this point of a data, you know, a data research process.
Yes, exactly. I cannot emphasize as much as I can to agree with what you're saying. Because we really are just dealing with like probabilities and frequencies and working with how often would we see a value like this. We really don't. And that's why we're using kind of all these types of terminology to say to what degree of certainty might we see something like this. So we can never really make like discrete claims. We can say like, this is the evidence to support something that we're observing, and talk about all the caveats that might exist around that. So I think that's a big part of statistics, is just using these frameworks of probabilities and like, what would you expect to see compared to what do you actually see, that actually would inform some type of decision. So it's good to know just like, what are the limitations, and then what are the strengths of this type of framework to inform your decision, and bringing it back to this framework that you just talked about. So yes, times 100. And I'm really glad you're here and us having this conversation, because this is really important, just as a takeaway from the class. So I'm really glad to hear that. And I think so where we left off was here in the demo, and I will just continue on from there. But thank you very much for these questions. And this is just doing the same thing we had above, now with a different critical value that we're looking for. So area under the curve being 0.05. And so we don't need to subtract from 1, because this is just calculating for B, because we're trying to find everything up until that value. And that's just by default what's returned in this case for critical value. So let me just show what that prints. So this is now looking for that other side of the curve, you know, something like here. It's looking for everything up until that value. So the area under the curve here is still that 0.05, but now kind of on the left side, if you're thinking about it, because we didn't subtract it from 1. And this would be, how many standard deviations away from the mean are you? So 0.27. And this is starting to get a little bit ahead of ourselves just from the lecture, what we've seen so far, but I will talk through it now, and then we will repeat this from the lecture slides, because the way we test the hypothesis is using the proportion difference. So bringing us back to how we would solve for this might be similar structure as you would see in a homework question, where they're just telling you, you know, here's the number of observations in group 1 compared to group 2. And you could either have that as a subset or just as 1 and 2. So this is just defining inputs that we would then use in a type of formula. So in this case, I am now just using what we walked through to create this upper critical value and lower critical value based off of the different inputs here. So define. And so now this is taking the the critical values that we looked at when we were just looking at one here. And it takes for, let's just say this was for the area on both sides of the curve. So that's why we're dividing by 2. And so we subtract 1 from each of the sample sizes for the degrees of freedom that we need to use. And this gets us to the upper and lower value. I think actually here we divide 1 divided by that because rather than subtracting from 1, but I need to just refresh exactly there. But I see a hand is raised.
Yes. So you subtracted -2 because there's 2 what are they called? The 2 DFs. I forgot the name of the
The degrees of freedom.
Degrees of freedom. There you go.
Yes, and I'm just reminding myself that that is the formula. If that is, let me go back to it's good to just refresh exactly, because sometimes I do this a little ahead of time. Because we're getting into, this is from 11.2. And I am just going to remind myself why we might subtract 2. Because I think it's just 1 that we should be subtracting from. Because this is essentially what we're now calculating. So let me just make sure what I have here is correct. And so you were asking, why are we subtracting 2 from here?
I was confirming that we're subtracting 2 because there's 2 degrees of freedom, right?
So I think we should actually only be subtracting 1 from both. And so I'm not sure why I have to subtract 2, because it should really just be subtract 1 from the top and 1 from the bottom.
You were testing us. I get it. Okay.
Yeah, definitely testing myself as well. And I sometimes make these things too fast and don't check myself enough. So I think it should actually just be subtract 1 from both. So let's change that. Yeah, I need to check myself. So before I publish this, I'll just go back and double check and see. Because even this, I'm kind of curious if this is equal to what we did before, where we just subtracted 1 from this value. I'm kind of curious if this would give us the same thing, because this is what we did up here. 1 minus instead of dividing, but it's slightly different. So, but, kind of relating back to the homework and for this class, I'm not too concerned about like the actual values itself. It's more so like the framework and how we approach things. And like, if you're putting in things in the right way, that's what I consider is more important compared to like the actual answer itself. So even if you subtract from 1 or divide it by 1, the values are pretty similar and you'll probably arrive at the same output. So Kenley, I don't remember why I divided here by 1 and subtracted by 1 in the other way. So I would want to just look more into it to see what are the differences here and what is what are the caveats of doing it one way or the other. But for now, as long as if you're trying to do above a value, I'll just keep this consistent and do 1 minus that, but maybe it's to divide by 1 instead. So I will just keep consistent to not have the 2, but I will make a note to myself. Look into differences of dividing by 1 versus subtracting. But essentially, as long as you have, this is something above that, we're just trying to account for the area under the curve on both sides. So we just have to subtract by 1 to get it to everything on this side of the tail compared to just using as is for everything on the left-hand side. So that's what we're just getting, that upper and lower. And then creating this confidence interval where we divide the proportion and then multiply it by anything that falls in the lower or the upper, because we are trying to see this proportional difference. So, and the textbook walks through this, and we'll walk through this next in the slides, but this is just how we would approach it using Python, where we're taking these like critical values. And now the key difference compared to the other hypothesis testing we were doing is to see if the value of 1 is in between the upper and lower bound, because we are trying to see, is this ratio, are we dividing 100 by 100 to get back to 1? Or are we starting to see there more actual variance that differs between these groups to a degree that's significant enough that it might reach the lower or upper bound area under the curve? So that is why we just test if 1 is between them. And so if 1 is between the lower and upper bound, then we do not reject the null hypothesis. But if it is not, then we would have evidence to, let me just talk through this a little bit more. So let's just say if we were trying to do this 95% confidence interval for the ratio population variance, because that's what our value of alpha was everything outside of that. And we see the variance differing between these two groups. And I'm just trying to get back to where these numbers were from. So we're seeing these values here, and it's a little different, probably because we subtracted 2 before, but I think it really should just be 1. So we're starting to see just like what is the ratio of population variance. And it's anywhere between this 0.11 and 1.21. So seeing that the variance between these two groups are between 13% and 120% of the variance of scores. So we see that 1 is between here, is between these values. So we do not have enough evidence to reject the null hypothesis. And once we go through the slides, I think that will kind of just become a little bit more clear as to why we do this. And then we can talk through more questions if that doesn't become more clear. But pretty much just how you would approach this is we're just testing if 1 is between the lower and upper bound of our confidence intervals. And that is how we approach this hypothesis testing framework. So we try to see if we take the variance of the first group and divide it by the variance of the other group. And if that is equal to 1, or if we're seeing if the value of 1 is between the upper and lower bound, because that's essentially saying the same thing here of being equal to 1, or if the value of 1 is between these values, because it's never going to exactly equal 1, but we pretty much just found from this type of test that the value of variance we found is somewhere in here. Like it did not go into the green areas to say there is a significant number difference in variance. So that's why we don't reject the null hypothesis, or we fail to reject the null hypothesis. There's not enough evidence to pertain to the alternative hypothesis to say that the variance of scores is significantly different enough. Even though we started to see these confidence intervals, how it relates back to the overall distribution is just not extreme enough for us to reject the null hypothesis. And this is I think getting back to the actual example that I took this from in the textbook, because this should be aligned with that. So let me also make a note to myself to find more context, but I believe what we'll be walking through next will show that. Because we just walked through a two-tailed test, which looks at the proportion differences and see if it's equal or not equal to 1. If we were doing a right-tailed or left-tailed test, we would take a similar approach, but look at if the proportion is less than 1 or greater than 1, and run that type of hypothesis testing framework in a similar way. But I would recommend walking through the textbook chapter on this, because they have these little exercises that go through the different examples for the confidence intervals. Yeah, this was that example question. So I see we have a little bit of a difference in our scores, and maybe when we subtracted 2, we got closer, which I'm kind of curious as to why. But we'll need to look, I'll look more into this before publishing, because really, let's see, or maybe when I had 1 divided by, we got closer rather than this. Yeah. Oh, okay. So maybe that's, so this is referencing from example 11.6. So we have 0.13 and 1.40, and that's what we see here. So let's go with this for approaching rather than subtracting 1. But again, if this was back to the real world, it would just be a little, you would probably, just want to do more research around things, but the difference wasn't super extreme. So we just would want to look more into which way to do it. But based off of what the textbook had here, this sample goes right with that. And so here walks through how we would, what we just talked through. And here are some other examples from the textbook, but we won't walk through now. But for the homeworks, it would be useful to walk through some of these as well for the one-tailed testing. And it walks through exactly how to do it. But again, it's pretty similar to what we just talked through. It's just the difference in being equal to or being less than or greater than.
So for those symbols that are like in the textbook that we can't make with the keyboard, it's okay if we just copy them and paste them, right?
I find it hard to actually copy and paste from the textbook directly. I've found like kind of some hacky shortcuts, like a plugin where you could copy and paste from a screen. And really in Python, it doesn't matter what variable you're using. Like, so you see, I've, instead of writing the Greek letter mu, I've just written mu to represent the mean. So
Yeah.
here, if you just want to do anything that makes sense to you and that makes sense to others, n usually represents the number of observations. But if you wanted to just do like n obs instead of n, it's up to you how you'd want to input it while you're working with it.
All right.
Yeah, so I like to have the right symbols in the markdown, but it's more so important to me that you understand the concepts rather than everything looking, mathematically as accurate as it can be. So I will leave it up to you, and I trust you guys. Any other questions though, just on kind of how we approach this? Because next I will just talk through a little bit more of an example. And we'll start.
Example would be great. I think I'm just thinking a lot about the process, just how to plug these things together. So just looking at an example would work well.
Sounds good. Yeah, let's walk through an example. And I'm just lingering on this, mostly just to refresh how this relates to what we've been doing previously, where just depending on the question, are we trying to say, are these two variances, similar to each other, or is one greater than the other and is one, less than the other? That's how you would use the right-tailed or the left-tailed test. So really, these questions all relate to comparing variances between two different groups. So from the example we were just trying to talk through, if we were trying to say, do the variances between the two class sections, let me get the question itself, just so we have a little bit more context from 11.6. This is students of two sections of a statistics course took a final, and we are looking into the variance between the two sections to see if there is a statistically significant difference between these two sections of class. And this could be interesting if perhaps one class started in the morning and the other class was at night, and you're interested, do students who take class at night perform better than students who took class in the morning? And you're kind of looking at how much does the grade vary between these two classes. And so this walks through what we just did in Python. And if you wanted to use the table to get these critical value scores, you also could do that. And in the textbook here, it walks through how you would do that. And so just the differences with these two different degrees of freedom and what you're trying to calculate for. So just now we have the context, we're trying to compare two different grades of classes. And we want to know, just do students perform differently between these two different class sections? And by differently, we're not looking like, what is the average test score? We're now looking at like how much variance existed between the two class sections. And this would be the way we would frame that hypothesis, where we're pretty much saying, is the proportion of the variances equal to 1? And this, again, just bringing it back to what we started with, are we taking 100 divided by 100 where we have the same value and it's bringing us to 1? Or did one class, have lots of variance and the other class had very little, and we actually see a significant difference between the two groups?
Those would be our null hypotheses and alternative hypotheses, right?
Exactly.
So the null would be that there was significant variance between the two groups, and the alternative would that there's not significant difference between the two groups.
It is the opposite, because we always want to start with innocent until proven guilty.
Okay.
And we always start with, we don't know anything about how anything works. We just want to find evidence to start to inform whatever hypothesis we're trying to create. So we're always starting out with this, H0 or H0 or the null hypothesis of saying there is no difference in the groups, or, jelly beans do not cause acne. And then we run experiments to see, does the variance between these two groups differ enough for us to have evidence to reject the null hypothesis? Like, this is evidence towards the alternative hypothesis. Or we found, jelly beans do have an effect on acne. So we have evidence to support the alternative hypothesis.
Okay, understood.
Yeah, and these concepts, it always helps to repeat it again and again. But I think if you can just think of this innocent until proven guilty, and the role of the statistician is almost the role of a lawyer to, to find evidence to reject the null hypothesis.
And so I really like that we're plugging this into like a real world interpretation. So if we've defined our null and alternative hypotheses, then this is a sigma, right? The
variance?
The variance 1 and variance 2. So we're dividing one variance from another equals 1, one variance from another does not equal 1.
Exactly.
Okay.
Exactly. And this even relates back to the class homework that was due last week, where we were looking at the proportions of means, and we were trying to see, does the proportions of two means differ enough in one group compared to the other group. This is now just taking that same approach, but now applying it to variance instead of mean.
I don't understand that.
Sure. Yeah, we because I didn't cover it explicitly in the lecture. It was just a homework question. And it was also the bonus from 2 homeworks ago of comparing like the proportion. So this is taking that same like proportion, if the proportion of one group, is the proportion, are we comparing something that's similar to each other, or are these two things very different from each other? So I just bring that up because instead of comparing the variance, you could also, compare the means of 2 different groups. And if the means are similar to each other, then we would start to see the value of 1. Because again, we're comparing, 100 to 100, this equals 1. Or is the mean of this group very different from the mean of this group, so that we see something that's not equal to 1. And I just bring that up because this is related back to other hypothesis testing and not necessarily like unique just to variance, but it's this framework of testing the differences between 2 different groups.
Right. So it's not just about calculating variances. We could find it using the mean. We could find we have different methods of going about calculating the 2 populations.
Exactly. That's all I'm trying to emphasize, because even you could bring this to like correlations and some other types of tests as well. So yes, just wanted to mention that this isn't unique to variance, but it's when you're comparing 2 different groups. So thank you for asking that question. And that brings us to the second part of this lecture, where we will now talk about these chi-square tests. So that was the last kind of like null hypothesis significance testing framework, where we're comparing, the variance between different groups. But now we'll be taking similar concepts and applying it to new questions, where we'll start to test different things, because one limitation from this framework is that it doesn't necessarily say like how much does the variance differ. It's more so just saying that they are different. So we kind of need to have other tools in our toolkit to start opining to more kind of granular questions, because we're kind of taking like the same tool, like when all you have is a hammer, everything looks like a nail. Now we want to start to get other tools in our tool belt so we can answer more specific questions. And that's what we're getting at now, where we can start to actually see, like how much variance exists. So this chi-square test is looking into how much did, sample proportions fit sample data, where this now gets us into understanding kind of expected frequency, even getting all the way back to like our probability chapter, which I think was module 2, where we can start to see these probabilities that we expected based off of, past data. How would this compare to what we actually observe? And we can start to use statistics to account for any differences. And if we were getting into regression testing, which would have been our last module for the class, this concept of reducing error between what you think would happen versus what you see is really like the core of a lot of regression, and even getting into like machine learning and how we apply this to like models of how things work. So just this concept of comparing the actual versus expected and trying to minimize the difference between those 2 things is really the goal of most of like applied statistics. So as long as you are obtaining from what I just said, where we're trying to compare like our framework of how we think things work compared to what actually is seen, and just through iterating against what we see and adjusting what we think will happen compared to what we're seeing, is how models are developed and tested, and you kind of want to monitor it over time so that you continue to minimize the error between what we think is going to happen and what we actually see. So this chi-square goodness of fit test is applied in regression and in a lot of other things that we might use. But for now, we're just kind of getting a taste of this approach and this test for how much did our sample proportions fit the data itself that we see. And we'll walk through this a little bit more. I'm just now kind of exposing you to these new tools in our toolkit, where the second test we'll be talking about is this test of independence, where we keep saying like independent and independently distributed. This tests if one sample is actually independent from another. So this is now getting into how we can test these assumptions we've just been taken for granted, by saying, hey, this value is normally distributed and independent from each other. We can start to use these tests to say, hey, is this sample actually independent from this sample? So just bringing it back to an example in last class when we were talking about male and female bikers using the city bike share program. And we just said these are independent from each other. We can actually use a chi-square test for independence to validate that assumption. And then lastly, this test for homogeneity is looking into, do two samples come from the same population? Like, are these things similar enough for us to assume that they are from the same population itself? So this is even getting into more kind of sophisticated questions that we have been taking for granted. And how do we calculate to test these different assumptions? So thinking about this goodness of fit, I think it's just always like kind of funny, like, oh my goodness of fit, we're just phrasing it in this way. We're trying to see, did the sample proportions of expected values fit the sample data? So let's just walk through a scenario of thinking about carbon emissions. And this is just a quote from Visual Capitalist saying, between 1965 to 2017, the top 20 companies have contributed 4,800,000 total carbon emission, or 35% of cumulative global emissions. So even just seeing like the top 20 companies are producing 35% of cumulative global emissions. And we might want to now test that Chevron contributes 11% of emissions out of the top 20 companies. So this was just some sample statistics from this graphic that I found, and just thinking, okay, let's now test that Chevron contributes 11%. So this would be just an example of the first test we're talking about, this goodness of fit, where we're trying to see, does this, how much does this change? So before we even conduct a test, we need to ensure that this random experiment does not violate some conditions that we are dependent upon to be able to run this experiment. So one of them would be that the samples are independent. So whatever Chevron is emitting is independent of ExxonMobil's contribution to the whole cumulative global emissions. And we also need to make sure the sum of probabilities all add up to 1. So if we're looking into this basket of 20 companies, we know that they should all add up to 1. If we were to add everything together, we should get to this value that we're trying to get a proportion from. And we also need to assume that the probability associated with each category remains the same. So we don't have any, kind of like a time series component to this where it's just, static type of probability that doesn't change over time. So we will run some types of experiments, such as, does the population proportion, is this equal between all categories? And that kind of gets at just seeing, is the proportion different between the different groups? And then we can actually test the specific expected proportion for each category. So one is kind of just this high level binary of, are the proportions equal to each other? Because that could then just inform, differences that exist. And then if we're actually trying to test one specific value, we can see what is that expected proportion compared to what we see in the data. So we can use our hypothesis testing framework to evaluate something like this. So for one example, is the population proportion of the top 5 contributors of carbon emissions equal? We can start to frame this as a null and alternative hypothesis that we can then start to test. So this is now looking into 5 different groups and comparing the proportion, saying that this is equal to 0.20, and that's just 0.20 because these are 5, and we would take 100 and divide it by 5, so that the proportion of each, to say each is equal to 0.20. So we're trying to just see, back to just this graphic, if for some reason we wanted to test that the top 5 contribute equally. This would be a way we would test that, where we're seeing, is the proportion of each equal to 0.20, because that would indicate that all 5 of these proportions are equal. And that is the null. And now we have this alternative of saying not all population proportions are equal. So we're trying to say, hey, Chevron has something that's different than, what ExxonMobil has. And this is an example of that second type of scenario where we would now want to have specific proportions that we're trying to test for the 5 contributors of carbon emissions. And we would have what we think they are based off this. And then the alternative would show, hey, there's something different going on here than what we would expect to see. So this is just walking through how we would translate different problems into different hypothesis testing frameworks for us to then go and test. So just depending on the problem, we would phrase it in different ways. Any questions just regarding how do we structure the null and alternative based off of these types of examples?
Can you go back to the alternative real quick?
On this slide?
Yeah, on the same question. Is there an alternative way of doing this?
And what do you mean by alternative way of doing this?
The last slide?
Oh, this one?
Yeah.
Oh, so these are
Okay.
just 2 separate examples asking 2 different questions, where one, I'm just saying these are like 2 different experiments we can take for this. And that first example just ran through testing if the population proportions are equal to each other. And the second example was testing an expected proportion for each category.
Okay. Okay, just to make sure that the criteria of the actual testing is met.
Exactly. So we just want to make sure that these things are like mutually exclusive from each other. And this null hypothesis is pretty much stating that things are equal, and we want to find evidence against this. So even getting back to like the F distribution, we were saying, like the means or the variance between these 2 different groups are equal to each other as the null. And something in the alternative, we'd have to find evidence to say, hey, these 2 things are not equal to each other. And they're not equal to a significant degree. And it's this significant for us to have evidence to reject the null hypothesis. So this is applying it in a slightly different way to say the proportion between the top 5 contributors are all equal to each other. And if we find evidence against this, we would need it to be extreme enough to reject the null hypothesis.
Okay, can you, for example, if the numbers did not add up to 100, then how would we adjust the experiment?
What do you mean by the numbers didn't equal 100?
Like for the next slide over, it looked like when we did the calculations, it all equal, okay, so it all came to 0.15. So then we feel we can move forward, right, with this testing?
So all of this approach of proportions of probability need to equal 100%. So even if I can get us back to even like chapter 2, when we were learning about probability, and you had like probability of an Olympian scoring gold, silver, or bronze, you also needed to have the probability that they won't score anything for us to use like rules of probability. So this is the same type of approach of, we need the probability of this type of proportion that we're trying to test. All of those things need to add up to 100%. So if this was a different example and things didn't add up to 100%, I think it would just need to frame the question, like what is it that you're looking at? Because usually it will equal 100%.
Okay, yes, I remember that everything needs to equal 100. Okay.
It's just because we're looking to break down the proportion between things and see, like, yeah, if you had, 5 groups, how do the proportions differ? But you need like the average to, not average, but you need the total to equal 100%, because we're dividing it into proportions.
Okay.
Yeah, good question to talk through, because it's not arbitrary that these things all add up to 1. It's required and kind of just, yeah, maybe even
Also-
one. Yep.
Also, because we're still in the testing phase, sometimes there's things we have to adjust about the test in order for the stats and the numbers to work out. So that's really, I like the way that these conversations are going, because we're talking more about adjustments that need to be made in a very early on part of a research phase.
Yes, definitely. Yeah, it really, we're just defining these things so that we can use our statistics on them. But I see what you're saying, because it is very like experimental, and we're defining things. It's in a lab, if this is like desk validation compared to, field validation.
Yeah, and also like scientists or business researchers, they adjust their tests all the time. So you're giving us questions and we're kind of like, taking it at face value. But if we're thinking more comprehensively about like the testing process that we're inside of, oftentimes tests are adjusted in order to become better, in order to be improved all the time.
Yeah, I mean, exactly. If you were to take this test and see how the proportions are different from each other, then you could kind of rinse and repeat, get a better test and evaluate that to get kind of closer to reality of what you would see. So yes, this is giving the kind of the tools to get to that point. So yeah, you kind of do continue to experiment and see like, hey, try this, try that. And almost like trial by error until you get to what makes sense in reality.
Did we go over whether it was a 2-tailed or a 1-tailed test? Yeah, I wasn't paying attention for like 2 minutes.
We have not. This is more so just walking through the questions. And this actually, I don't think even really gets into 2-tailed or 1-tail anymore, because we're pretty much just looking into actual versus expected. So what we were talking about before, from the F distribution, we'll have 2-tail and 1-tail. But now we've moved on to these chi-square goodness of fit tests. And it's really just seeing like, is it or is it not? So kind of more of like a 2-tailed test compared to a 1-tailed test.
Okay, because number 2, it says determine whether this is a 1 or 2. That's what.
Got you. Yeah, I've just used the same type of intro for any null hypothesis significance testing, because again, this is more so like a tool in your toolkit if we were applying this to something else, just knowing, hey, we should think, is this a 1 or a 2-tailed test? But the majority of the time, we should know by now, like how to know if it's a 1 or a 2-tailed test. And in this case, we're trying to just see, are things equal to a value? And so we know that that's a 2-tailed test, because it could be something greater than or less than. But if this was, trying to see are these less than 20%, then that would be a one-tailed test. So I just have these numbers here because this is the same type of approach, no matter, whatever hypothesis we're trying to test. Any other questions? Okay, so this is just to walk through that and how do we actually calculate something from this? So let's just say, kind of Mara, what you were talking about, if someone from like your analyst team was saying like, this is what I think the proportion of the top 5 contributors of carbon emissions is, then we can actually experiment and use a sample of data that we go out and try to calculate. Let's say we're trying to do some type of, environmental compliance checks, and we had access to sample carbon emissions from these 5 different companies. And we can actually start to get the proportions between them. We can now test, are the proportions different enough to fight against that first example we were looking at. But if we were trying to test this experiment to say not all population proportions are equal to their hypotheses values, we can now test the differences between what we would expect to see and applying that to the full sample of what we saw. So this is just an example if we were to, I think, look at, the student tests between 2 different groups. And what's the differences. I'm just trying to think like where this breakdown goes from, but really this is just visualizing if we had the proportion, let's say this is for exam results on a test, and 15% are excellent, 30% are good, 45% are fair, and 10% are poor. If we had a total population, if we added all of these up, we would multiply that by each value to get to the sample results. So I'm just going to add these up now just so we can walk through this, but this is really just that aspect of how we take a full proportion and divide it by each. So I just added up 46, 83, 105, and plus 16, and that's 250 total. So this, I'm just trying to explain what we're seeing on the graph on the slide here. So if you had, 250 students and 15% scored excellent, so we take 250 times 0.15, that gets us to, so we would expect to see 37% score excellent, and when we see 46 in the sample results. So this would, now we would compare how different is 46 from what we would expect to see of 37.5 to know, hey, did this proportion vary greater than anticipated, or to a degree that we should reject our null hypothesis to say what we thought it was going to be equal to. Does that make sense here?
Yeah. So at what point would it be too much? Because the difference between what was it, 46 and what was the other number? 37?
37.5.
That's like kind of big. So would we consider that to be failed?
Right. That's when we would need to use our level of significance to know, hey, is this kind of just in that, I'm going to jump back a lot, but I'm just using this to visualize, like, is that difference somewhere here? Like, is that normal to see because it's in like the majority of values, or is it so far away from what we would expect to see that it's something that's significant to give us evidence to say only if something was really awry here, did we see a value that extreme? And that's why we're using this whole framework to say, hey, how far is too far for us to say something is going on here? Did that answer the question?
Yes.
Okay. So even kind of thinking how this, and I saw the next slide, because this is talking about a case study rather than student tests. I'm just going to totally switch the example to give more context as to how this would relate to real world. So let's say you are the owner of a restaurant and you want to see if you should update your menu because you think it would increase sales if you changed your menu to be perhaps more aesthetic or just organize things. So you ask different patrons to rate the quality of your entrees based off of, the menu that you see. So each percentage responding is the sample proportion. And then let's say of what you thought, the entrees were. So most of them, think they're good or fair. And now let's say you revamp the menu and you ask the same questions and you want to see if there is a change in the population proportion as a result of you, improving your menu. So you would want to test, this is what we saw before, it was 15%. And now we have 46 patrons saying, hey, the menu, like the entrees look excellent. So is this a significant difference compared to where you were? To say, hey, the menu update actually improved, people's perception of your food. So we would want to know, like, how far away from 15% do we need to be to say, based off this experiment, the menu made a significant difference? Or is it kind of just by chance that you saw 46 people liking the entrees after, and maybe it was kind of just random that we got that value? So that's why we use statistics and this confidence interval to know, like, how extreme is this value? Because 46 might not be extreme enough for us to say there's a significant difference here. And at this point, I'm kind of just like repeating similar things just to nail this concept home of what it is that we're actually testing for here. And so now the way we would calculate this, where we have these would be the expected for the null hypothesis compared to what we then ended up seeing as a result of our little experiment. So we would expect 15%. So what I just calculated, if before they updated the menu, we would just multiply the total of 250 by 15. And we would expect to see 37.5 of excellent responses, but we observed 46. So Darren, as you were mentioning, is this 46 far enough from 37 for us to say with significant, evidence that, hey, the menu actually improved our perception of excellence? So that is just an example of when we would want to use this, and we would use this goodness of fit test to evaluate using our framework. So similar to what we've been doing this whole time of getting a test statistic based off of whatever question it is we're asking, this would be the test statistic for a goodness of fit test, where we were starting to see how much do things vary from the expected value. So here we see O and E, and that's looking at how much does the expected value vary from the observed, and we take the squared difference and divide it by the expected value. And this should look familiar with like sum of squares error, or the MSE, and we'll also be starting to use this in ANOVA. And if anyone has done regression testing, a lot of this same type of formula will start to be very familiar, where we're just, even when we were in like the Z-score, not to confuse with getting other stuff involved, but we're trying to see like how much does the observed vary from expected? And we use this type of formula for that. So I brought up the Z-score because we were kind of seeing like the value of X subtracted by the mean divided by what we'd expect to see. So I just kind of bring that up because these things are all very similar to each other of what it is that we're trying to calculate for. So in this case, we're just seeing like how close to the observed value did our expected value become. And we use this square to see how far away is it in like kind of relative terms, and then divide it by the total expected. So Just one thing to note, this test is valid when the expected frequencies for each category are 5 or more. So if we have less than 5, we wouldn't be able to use this formula, and we would probably want to just start to test using something else, a different type of hypothesis test. But in this case, and for the homework and for the class, we'll always have 5 or more. And the way we would break this down, so we could calculate this by hand by just taking the hypothesized proportion and applying that to what we did see. So what we would expect based off of our hypothesis for all these different values. So this was just walking through what I said by hand when I was calculating that, where these would be the expected ones. And then we subtract that from what we actually saw. And that's what's being plugged in here for each of our different groups. And we get this value of 6.520. So just to talk through some things, the sum of expected frequencies must equal the sample size. And that's just because we are taking our total number of observations and multiplying it by each proportion. So that should all equal back to the total number of observations. And that's kind of getting back at the question, Mary, you had of like, why do these all need to equal 100? And really, it's just, they usually will because we're taking the different proportions and adding them back up together. And we are just trying to compare how it would look like against the hypothesized value. And the chi-square statistic measures how much the observed frequencies deviate from the expected frequencies. And essentially, the closer to 0 the value is that we're calculating, so we got a value of 6.520, but the closer to 0 means the smaller the errors. So back to the mean squared error, the closer the error is to 0 means that the observed and the expected were pretty much right aligned with each other, and we didn't have a main difference. So if we were trying to say, you know, that we expected to see 37.5 and we saw 38, that would be less of an error than what we saw with 46. So this is just getting into how do we interpret the value of this output. We want to get as close as we can to 0 here. But also it kind of depends on how accurate you want to get. You know, if you were trying to say the delivery of a package will arrive between 1 to 2 days, and then you could see when it does arrive. But if you were to say a package will arrive between 3 p.m. and 3:30 on Monday, that would be harder to get right exactly at the same time. So kind of just depending on what degree of granularity are we trying to get. I'm just bringing that up because based on the context of the question, these things might change. And pretty much we're just trying to get as close as we can to the actual value. And these are, we would reject the null hypothesis when the chi-square value is significantly greater than 0. And when we're talking about left or right hand tests, these are actually always right-tailed tests because there actually isn't the left tail, because this will always be either 0 or positive. So we don't need to, so this isn't really a two-tailed test because it will never be less than 0. So even just answering that question in 2 here, this will always be, so I'm kind of contradicting myself a bit because these are always a one-tailed test to see if it's greater than 0. And we'll walk through a demo of how to calculate that. And just one limitation, similar to what we've been talking about, is that we're only measuring if the population proportions equal the hypothesized value. We don't know which proportions differs from the value. So we know that our hypothesis about the breakdown, you know, of carbon emitters might be wrong, but we don't know which proportion we didn't get right. And once we get into ANOVA testing, we'll be able to actually get more into those different insights. But at this point, we're still just knowing, hey, do we get it right or did we get it wrong? And then we could readjust and perhaps make a new experiment from there. And so we can calculate this test statistic as what I just showed below, where we got this value of 6.52. And we could use our table to calculate the p-value from this. And knowing that using from the table with degrees of freedom here being 3, because we have 4 different groups. So we subtract 1 for the degrees of freedom. So we're having degrees of freedom equal 3 here. So we can use the table to find the like our p-value here that we need to use. And so I just have my notes here, but we'll walk through in Python how we would get to this. But the p-value here, if we were to use the table, would fall between 0.05 and 0.10. So if we were to establish an alpha at 5%, we would fail to reject the null hypothesis, since our p-value is between 0.05 and 0.10. But let's walk through this to show what that looks like. And just one thing to note, if the frequency of a group falls below 5, we would not be able to use the chi-square test. So we would combine these categories to achieve the results. And by that point, when I'm saying frequency of a group falls below 5, let's say we had, for poor, there was only, 3 values that fell here, we would need to combine poor and fair into one group. But because all of these frequencies are over 5, we don't need to consolidate anything. Okay, so let's walk through this example where we will look at this example about share price. So what I'm showing you here is just if you actually have ever downloaded the full file from the homework and you've seen in Excel that there's lots of different tabs, this is just some Python code to see like what are all the sheet names that exist in an Excel file. So that way you can read in the file that you're showing. So another way to do this is just the consistent way we have been doing it, where you use pandas to read in the file and you list the sheet name of share. So if I just wanted to show that, this would be pd.read Excel. And I'm just showing you another way of doing it, but I will also just show you the way we've seen it, just so you have that one-to-one comparison. So this is just emphasizing what the sheet name is, but let's say, this was something where Excel crashes because these files are giant and you can't open them. You can use Python to open them instead. So I don't know if folks at work deal with data or if they deal with large data, but a lot of times, sometimes Excel can't handle that. So this would be a nice way of parsing large data just to even start working with it. So these things are exactly the same, and I'll just show you that by looking at the head of what it is we're working with. And if I were to read this in, let me just write this as test. And then let me just show you test.head. We would expect these two things to be exactly the same. So I will delete that. And I'll leave this as a comment. How we usually import. Okay. So we have this example where we have 4 different market shares between a firm, and we're trying to see if something has changed as a result of time. So this was something from recent customers, trying to see if these are different from the 2019 analyst report. So even just to show, all we have here is what we're seeing here. So we have this expected market share from a 2019 analyst report between 4 different firms. And then we have the number of recent customers that exist. And I would assume that this recent customers tab all equals the total number of responses that we have of 200. And so let's walk through how we would answer this question. So we have 200 observations, so we can even just define this as n, because I assume we're going to need this, but I'm just talking through as if, you know, as if I've never seen this before. Maybe what are some things I would start to think about for framing this. Number of observations. Let me just have that here. So let's just say our question here is this will be very similar to what the homework will look like, where you'll first need to establish the null and alternative, where here the null would be what our expected market share would be between these four firms. And we will use this value to test against each observation. For the null and alternative, where the alternative is not all market shares are equal to their hypotheses valued. So this is creating that value of n that I just found. So this is just another way to specify that column. So from the data frame, this is the total number of observations. And this column here creates a list, and it iterates between each value of recent customers. And divide it by the total sum or n. So this little list comprehension takes each value for I. So I'll just bring this out here because this is really handy for when we're doing lots of things over and over again. So you could say for any value of I in this column, this is just returning it. So we see that here. So 70, 60, 54, 16. But even if we wanted to, you know, +5 for each, this is this list comprehension. So we can do lots of things on this column and save it as a list. So in this case, I just divided each value in this column by 200, which was n. So we can create a new column of what the expected value is in this, of the observed proportions. So even let me just add this as a column in our data set, just so we can see even some more like data wrangling things that we might expect. So just one way of doing this, observed prop. Let's see if this lets us do it. This is me creating a new column. That would just be those values. So if we were to rerun this, we would see how those values we just took, which was pretty much just dividing each of these recent customers by the total number of observations, and seeing now how this compares with that market share of what we saw. And then we'll use this framework to see how much things deviated. So another thing that we'll need to calculate is what the expected value would be for each value. So now we're taking this value for each ones and multiplying it by the total to get what that value would be of expected value. So let me also add that just so we can look at it all together as a data frame rather than these little lists. So I'm creating a new column. Yes, Mary, you have a question?
Yes, when you're pulling out observed proportions, I'm not sure, you know, the distinction between observed proportions and total sum. You know, I assume we're observing all of these columns, so why create a separate column for observed proportions?
So the question is, why create this column, or?
Yes.
I just created this as a column in the data frame, mostly for demonstrative purposes, but also because we'll be using these values of this observed proportion when we were, I believe, when are we actually using this? I guess you don't really need it. But let me check myself before I say that. Yeah, I don't think you actually need it, because this is just seeing like what are the observed proportions. So really it's kind of just for context sake, because really you just, all you need is this expected value and subtracting it from what you did see. But this is just, I think it's good context to know how does this compare, because then when you're starting to test the hypothesis, it's good to know, kind of what you would expect to see just from your own intuition. For me, without really knowing much about the total distribution, but thinking like, okay, 0.30 is close to 0.32, and we saw 64 compared to 60. So it just kind of helps to put things into perspective, but it's not necessarily required for the formula.
I'm just a little bit confused about when we're looking at observed proportions versus expected value. Can you just explain in the context of this particular test, like what that means for this?
Yeah. So we have this starting point of what we think the market share will be. And then we conduct an experiment to see how many customers went to the 4 different firms. And because of this difference, we would have, let me just even walk through with the code here. So we took each value of what we saw from the recent customers and divided it by total, just to create, based off of this sample that we took, based off our experiment, this was the breakdown of market share from our experiment. So if we were to take another experiment, we would see a different observed proportion, and maybe, we can start to continue to take new experiments and have more tests to see, do these values vary enough from what we thought they would be to either support or reject the null hypothesis. So that's why I brought it here, where we're now seeing, like, based off of this experiment, what was the proportion difference. And then I have this expected value to calculate for use of our formula. So this one was the actually needed one to say, had we just gone with our expectations, like our hypothesis, and times 0.4 by 200, we would have expected to see 80, but really we only saw 70. So we know that there was some error in between the expected and what we saw for this firm 1, compared to firm 2, where we expected 60. We expected 64 and we saw 60. So that error was a little bit less severe as compared to firm 1. And then we could look between these two things, where even for firm 4, we got that very wrong, where we thought there was going to be 8 and we actually saw 16. So the observed proportion was this when we thought it was going to be 0.04.
Okay, so back to observed proportion. Is that the amount of the market share that we've actually tested within the experiment?
Exactly.
And so when we look at recent customers, that's actually the number that's come out, but we expected it to be 8.0. Instead, it came out as 16. So I guess for line 4, if the market share was 0.04, we observed 0.08 of that market share. The customers that we got from that was 16, but we expected them to be 8.
Yes,
So that's kind of like the process of the experiment.
exactly.
Okay. Got it.
And let me. Yeah,
And
let's
since
see.
it was 16 instead of 8, that's way more.
Exactly. So we are looking at like these relative differences between, but for the sake of our hypothesis, we are aggregating all of those differences together. So even if, even if one had extreme differences from the expected, that would do enough damage to give us more evidence to say against our null hypothesis. So that's kind of why that caveat of this test doesn't really say like, how does each group vary? It's more so as like a zero sum game of like, there was too much variation from the expected compared to the actual. And it didn't matter like which group it came from. It exists. So therefore we have evidence to accept or reject the null hypothesis.
And that would be a major insight that our expected values were like 50% less than the actual numbers that came out. So we'd be just observing how we ran the experiment, that we were like, we expected it to be half the amount that it actually was.
That would need to get into, I think that would need more testing to make that type of evaluation against like one of these specific values varied, by half. What we're doing here is just saying like it varied from what we expected, and it varied by amount that's significant enough, but we can't necessarily say like by half, because again, this could just be like one experiment. And we would want to perhaps just collect more information about this last firm. But, just by doing this type of approach, we see this one varied very significantly from there. But this type of test is, again, looking at as a whole, as like a zero sum game. We're not testing like, does this one vary significantly different from the rest? That gets more into ANOVA, what we'll be getting into next week.
Okay, so when in doubt with insights, make more generalizations about what you're seeing versus calculations, because we're not really concluding anything just yet. We're just observing inside of our insights.
Exactly. And that's why it's so important for us to structure our null and alternative hypothesis in this type of very like narrow scope of a lens, because we need to stay general with our hypothesis and our experiment.
Great.
That is why it's like kind of this zero sum game. Either all of these proportions are equal to what we expected, or none of them are. Because again, that's kind of just like this tool in our tool belt that we are developing. It kind of just does this one specific thing. So we would need a different tool to kind of get at other things. But now we're at the point where we'll be able to use this chi-square, which is a very handy function that provides pretty much everything we need for this type of goodness of fit test, because it calculates the everything we would need. It has our observations. When I say it calculates everything we need, it does a lot of the heavy lifting for us to provide us the p-value and the expected result. So we would input what we observed here. And again, all this documentation you could be found by clicking something like this, which would show you what we're inputting into this function that SciPy created for us. So we have our observed frequencies and then the expected frequencies. So we just had to do the heavy lifting to calculate those expected. And then we have this degree of freedom, which just needs a little bit of thinking. Like we have 4 different groups. Therefore, we need to subtract by 1. So we can account for not, so even just thinking about back to degrees of freedom, because we're trying to calculate how different each proportion is. And if we have 3 of them and we have the total amount of variance, we don't even need to calculate the last one, because it's by default, because everything should add up to the total number of observations. So I'm just bringing that up again of like why degrees of freedom comes into play here, is because we're looking at how everything all adds up to 1, and we need to take out 1 so that we have this validity of our calculation. And this axis equals 0 is probably by default, where you won't need to change that too much, but that's pretty much just, let's see actually what the documentation says for the axis. All right, actually, I don't even think we need this here. This is really just how do you want to apply the data to the array, because we have here as like an array of the data frame of expected values and such. So this is just saying like go one by one, go by one in the list. So we have our result from here, and we also, from this, by why I say it does the heavy lifting, we don't need to calculate the p-score because it actually calculates it for us here, but it's giving us a value of nan. So we actually do need to use the p-value from the same thing that we were using before, like the 1 minus the cumulative density function. And I'm not too sure why it replies with not a number here from here. And I assume maybe, okay. Probably need to look more into why that was not returning a value, because usually it would return something. Let me see. Well, anyway, I'm not gonna belabor it too much because we can just use what we have been using before of this, either with the survival function or 1 minus the CDF should get us the same value, or pretty much the same. And just have this degrees of freedom parameter here to get us this p-value. So if we were to set our alpha, which we didn't do, let's just say our value of alpha. So this is me as an example of what not to do. We first would want to set our alpha ahead of time. So let's just do of like 0.05 or, significance of 95%. So this value of 0.05, we're pretty much testing if, where does our value fall? So this is based off of the T table, not based off of what we found in using Python. So just from the textbook, it'll have this type of language and how you would use the value from the table, because you won't have exact counts, but you would use if it falls below or above from this value of 10.25 from the table. So you're kind of limited to the level of granularity, but here we have the exact value. So if we wanted to, pretty much test, so our value here, so let's do like p-value is equal to that. So if our p-value is less than here, we are able to have evidence to reject the null hypothesis. And this is even just bringing us back to here. Like we can just copy and paste. The reason you've seen it different in all the different times is because it kind of just depends on how you phrase it, that they're all equivalent to each other. It's kind of looking if things are, anyway, I'm not gonna repeat that too many more times. Let me just put this here, because they're all saying the same thing. If the p-value is less than alpha, we found that there's significant evidence, but if it's greater than alpha, we fail to reject. So I'm just putting this here because the reason why I say it's the same thing, just switched. This is now just saying, as long as the p-value is less than the value of alpha we established, I'm just going to write this is an equivalent. But this is essentially giving us evidence to say this value was extreme enough that it exceeded our threshold of 5% significance level, to conclude that not all values are equal to what we expected in the null hypothesis. So the way we would conclude this type of experiment is that we have evidence to reject the null hypothesis, and we can now state that not all market shares are equal to their hypothesized values. But a really key limitation here, we don't know how much each proportion differed from their hypothesized value. And for that, we'll need ANOVA to get to. But given just the scaffolding of the structure of our tests, this is what we can conclude. Any questions?
The alpha is the significance. Is that correct?
Yes, that the
Okay.
alpha is determined by how much area under the curve. You know, are things kind of near the mean, or is it so extreme that it's so many standard deviations away from the mean, it's in the tails, to a degree that we would only see a value this extreme given random chance. You know, if we were 99%, it would be 1 out of 100 just by random chance, but we did see it. So therefore there's something significant happening here. So this exceeded that threshold of 0.05 or a significance of 95% to say, hey, this value was so far away that it exceeded this threshold. And therefore,
Okay.
reject the null hypothesis.
And going back to what you were demonstrating to us earlier about how to look at a chart. So if the significance is 95%, we're saying that the point that we're looking at would be even greater than the entire graph being shaded as 95.
Exactly.
So it's part of that smaller tail portion. And so if the p-value is greater than the significance, that means it's in that really small tail portion. And that means that we're done because we know what now about the p-value.
We know, yeah, exactly.
What can we infer about that p-value now?
The thing, and I love us like bringing this all back together, because yes, exactly. And the thing that you can take away is that the probability of seeing a value at least as extreme as what we saw due to random chance is so rare. And we saw it. We had a value so far away from the, the expected value. And I guess I shouldn't conflate terms. Like, we are in the tail by so much. That means that there's something significant going on here, that the values do not all equal the proportions of what we observed, that they are different enough that we can state that we have evidence against the null hypothesis. So really that's the insight we have here, is we found the point on the curve of where the test statistic fell, and it is so extreme that it passed our threshold. And the insight we can draw from there is we saw a value so extreme that either this is just due to random chance that it happened, because, something random could happen for you to see a value that extreme, or it's because there's something significant happening here. So that's why we kind of just need to be careful with, you never want to say like with a 95% confidence type of thing. It's more so like 95 out of 100 times, you would not see a value this extreme due to random chance. So it's just kind of phrasing it in a way that gives us like kind of removes liability from the scientist as a statement, where you say like, I saw a value this extreme, and you would only see something this extreme due to chance, very rare, and we saw it, therefore there's something significant going on here. And this gets into even like p-values, where someone might say like, oh, the p-value was so small, but the way you interpret the p-value, I'm really glad that it seems like what you're saying, like that's how to interpret this p-value. And I think just in general, p-values are taken and communicated in not a accurate way, where sometimes it's like, this p-value is like a significance score where it's not really that value. of what we're thinking. It's like at least as extreme as what we're seeing, like thinking more in terms of probability rather than this is like a discrete value that you can take at face value.
Mhm. What was the original null hypothesis on this problem?
The original null hypothesis was saying that each of these proportions was equal to what the analyst, suggested.
Okay. Okay, so then we know that it likely is not. So I'm just trying to wrap this up like all in my mind.
Yeah, for sure. So we found evidence based off of what we expected to happen. And I'm just going to go to the data frame.
Mhm.
We expected this as an analyst, or, let's say, the executive team said this would be the proportion of market share. And then we ran an experiment that found this proportional breakdown of what we observed. And then we used statistics to calculate, does this differ enough to say that what we saw in the field, varied significantly from what we expected to happen? And because we got this value of 10.25, this is far away from 0, which would say like there is no, we got it exactly right, where all these values equal what we expected them to be. But, they varied too much, where they varied far enough where our value was a p-value of a significance, of 0.01, which is less than our alpha that we established before of 0.05. So it exceeded that threshold to say we would only see a value of 10.25 due to random chance, 1 out of 100, but we saw it here, which means that there's something significant going on here, with the caveat that this could have just been due to random chance. But the likelihood of it being random chance is very low because it is so extreme.
Definitely, that's a very low percentage for chance. Okay.
And that gets us just back to like the insight is really just based off of this binary. Either things are what we expected it to be, which is like you're innocent until proven guilty. After we conducted our experiment and we found evidence to say, hey, there's something else going on here, and something else happened and it was extremely different from what we expected to a degree that this would only happen due to random chance, 1% of the time. And therefore it is significant because that random chance is really low. And therefore we can say like, hey, from this experiment, we found a difference in the proportion. So, your analyst needs to revisit the market share because what we saw in real life varied too much.
Okay, I get that the analyst would need to revisit it, but they're revisiting it based on a 0.01 chance that the shares do not equal 100.
That these shares do not equal what the market share expected them to equal.
Okay. And so this is just about, being scrupulous and knowing that 0.01 needs to be looked into.
Knowing that because we saw such a difference compared to what we expected from using this chi-square test, we got a value of 10.25. And based off of this value, this is so far away from 0 that we would say, hey, you got it wrong. And we're confident that you got it wrong because it's so far away from what we would have expected to see. So we don't know exactly how they got it wrong. We just know that you got it wrong because the expected compared to what we observed was just too different. There was too much error for us to say, hey, you got it right enough for us to accept this null hypothesis that the market share is indeed what you think it is.
Okay.
Yeah, I think it's kind of fun because you get to like test, like, this is my perception of the world. And then you go out and collect data and see how much did my perception meet expectations. And we can use statistics to give like a quantitative value of, how right did you need to be in order to, accept your prior, essentially. And this is saying, hey, you got it too wrong. You need to adjust your prior and, perhaps update it using like what you did observe or like the posterior of what you saw. But I'm getting into kind of like stuff around like Bayesian stuff again, but kind of just like this framework of thinking of like, this is what I thought was going to happen. This is what happened. Let's go back to the drawing board until we get it right.
Mhm.
So we have two other tests to cover. So I'm going to get into that next. But a lot of these things, it's kind of like once we get the understanding, it's now just like experimenting with other stuff. So this is another handy tool that would compare the difference between groups. And this is now looking for, is the relationship between two like categorical variables, what is the relationship? Are we seeing the frequency? Is it similar between two different groups, or is one sample independent or different enough from the other? So one example would be, doctors investigating whether a new vaccine is equally effective for different age groups. We'd want to see, is age independent in different groups? Are 14 to 20-year-olds statistically significantly different from, 80 to 90-year-olds? So we're trying to see, like, are these samples independent from each other? So bring us back to even just like what we looked at in last class when we were looking at male versus female bike riders. We just assumed that they were independent, but if we wanted to actually test that they're independent, we now have the understanding and the framework to do that. So we can use our hypothesis testing framework. Either our null hypothesis is that these variables are independent. And our alternative is, once we find evidence to say that they are not independent, that would mean that they are dependent on each other. So thinking about how the frequencies of two categorical values of X and Y, and we had, contingency tables that we started to use to see what is the frequency for each categorical variable of how often we saw it. So I think just for recollection's sake, I think we were looking into like gym frequencies for different groups. But in this case, this is just looking into the enrollment and age of folks who go to the gym if they're enrolled. So even just like similar to the previous test, we're calculating if the frequencies between them are what we would expect to see. But in this case, we're kind of looking to see if there is a relationship between age and enrollment, what the frequency would be, and compare this against what we would expect to see if there was a relationship. And we use the test statistic to compute this in a similar way. So just walking through, we would have a way to calculate what the expected frequency would be. We can take the sum of each row and column and calculate these marginal row probabilities given the different groups. So this is just a little bit of a refresh from using contingency tables to break down, given a population broken into different groups. So in this case, this would be age group. And now we're comparing how many enrolled versus not enrolled in the gym. And now we can use these types of inputs to calculate, is there a significant difference between, people who are under 30 compared to people who are between 30 and 50 compared to people who are over 50. And this definitely pairs nicely with where we're going to end the semester of analysis of variance, because we'll be taking a similar type of approach of looking like differences between groups, and even relating to like A/B testing if you're bringing this back to other applications. And the way we calculate this This is pretty similar to when we were even just calculating some of the conditional probabilities, where we would take the sum and divide that by the total sample size to create like these marginal probabilities. So this is all very similar to what we did when we were first learning about probability, where we were calculating, for each row, for each column, what is the expected probability if you slice and dice the data in all these different ways. So more of this is in the textbook for walking through, and these are the steps for how we would start to calculate what the expected probability would be for the different group based off what we saw. So we calculate this for the rows and the columns. And this is exactly what we did back when we were first introducing probability. And we multiply, the different joint probabilities for, both enrollment and age group. And because we're using the multiplication rule for independent events. And so based off of this probability, given that these two things are independent, we can now start to compare what that would look like as a hypothesis. So we take this joint probability or the expected, number of customers to enroll compared to not enroll given their age, and multiply that by the total population that sees that value. So this was just, again, just kind of a lot of steps to get at this understanding of, given an age group, what's the probability that someone would enroll or not enroll? And we're trying to test if there is a significant difference between these different proportions for us to say that they are independent of each other. So if we were like break this down and these values were very similar to each other, we would say, hey, these are independent, these are not independent of each other. People who are 30 is very similar to people who are between 30 to 50 when it comes to enrollment. Or even bringing back to like the bike example, if men and women bike very similarly, there's no reason to treat these as two independent variables. They should just be considered one. And we use the same type of chi-square test statistic that we just learned, but this is a different type of calculation that uses the contingency table to calculate all the differences between what you would expect to see. And we would use the same difference between the expected versus observed. So that same squared difference divided by what's expected. And now we just have different inputs. So we'll go back to the demo to walk through how we would use this next type of independence, or actually, I don't even think I have it here because, yeah, okay. No, it is right here. No. I think this is something a little different. So let's keep walking through this, because I think this actually is the same thing when we're talking about independence and normality. Let me just check. Okay, no, we have it here. Okay. So we are now going to go through an example of how we test for independence. And later we'll be talking about homogeneity and this Yark-Bera test. So that will bring us to the end of the class. So in this case, we're trying to test for independence between, this is something for teacher ratings. This is something looking into impact of beauty on instructors, teachers ratings. I just got some interesting data. This is some question. Let's think, like, does the gender of a teacher, is this independent of if the teacher will receive tenure or not? So this is a sample of 463 teachers, and this is just some context at a 10% significance level. Let's determine whether gender, if there's a difference between teachers who reach tenure based off of their gender. So we will look into that. So our null hypothesis is that Gender is, there is some type of, these are independent of each other, where, gender and tenure do not have any relationship, compared to our alternative is that they are dependent on each other, so that there is a significant difference between teachers who receive tenure depending on being male or female. So this is just kind of an experiment that I came up with that I thought could be interesting given this sample data set. And so for a case study for bonus in this class, you could kind of come up with something similar based off of your own interest or work experience that you'd want to test. So I am just getting the number of values for tenure compared to gender, and we'll create a contingency table between these two things. Okay, and I have an error here because this DF is just out of date. It's looking for that other data frame we created. So it was saying you don't have this column, but we do. And I just need to go charge my laptop. So I'm just going to, it might die before we get to the end of this. One moment, I'm just going to pause my screen. Maybe if you guys want to take a quick break, I will just be grabbing my charger. One moment.
Okay.
Okay.
Okay, we are back and we are charging, so we will not have any more issues. Okay, are you both here?
Yes.
Okay, perfect, cool. All right, and Darren, see if you're there. But I might just keep walking through just for the sake of time. Hope you're with us. So let us walk through how we would use that same expected. So we are now using this type of chi contingency, which is exactly the test we need for this type of question. So this kind of just goes to show there's a lot of tools and functions that might do exactly what it is that we're looking for. It's just knowing how to work with it to get what we need. But in this case, this actually does all of the different parts just using this one already built-in function. We just need to get the data in the right format using this contingency table. And then this will actually calculate all of the different things we need. And even give us like the degrees of freedom. So this does, it calculates, there's just 1 degree of freedom because these 2 different groups. Let's see what this value of G and P are. So these are giving us the different test statistics values of, this is the lower and upper bound of the area that we would see. And these are the expected values given the frequency from this test statistic. So, and I have this math here that pretty much calculates between what we would expect. So we have this 50 plus 1.45 to get, there's 195, 52 plus 216 for how many male that there are. And now given no tenure versus yes tenure, we have these 2 different groups of 120 versus 361. And this is just calculating how we would take the total of, female times by how many we did see. of this for tenure. So how many women times how many tenure divided by the total length. So this is just calculating all of those different, marginal probabilities given what you see here. And this is just calculating that for us. So this is just to show you manually how you would get to those same values. And this just does all of that for us because you would need to calculate this for each, each square in this contingency table. I think there's another way of doing this just by saying like margin equals true. Is that correct? Maybe it's margins, which is, yeah, it's just calculating the margins where it's now taking and dividing by what you would expect to see of how many total observations there are. Yes.
Just want to ask a quick question. So the G is the upper bound and the P is the lower bound?
So let me get that right, because that might not be correct. Let me look into, and I think I should be careful before I just say the lower bound, because that sounded right to me. But let's see what actually is resulting from here. Of like, what does it actually return? Okay. So I was wrong. It is not the lower and upper bound, because that also doesn't make sense given that these should all be like right-tailed tests again, or kind of shouldn't even be thinking that way. It's more just like straightforward. We don't even need to think about that. It's kind of just as long as we're using this chi-square contingency table, we have this test statistic is that first value of what G is, and P is the P value that we have. So we don't even need to use the table to think about one tail or two tail. So the P value is just given. So let me make this a little bit more clear so I don't run into that assumption in the future. Thank you for calling me out on that. And this one is like the test statistic.
No problem. Just trying to get clear on what everything means here.
Yeah, no, I could have better practices here. You shouldn't really name anything like just G. I have no idea what that meant. So yeah, that would make it a little bit more clear.
Okay. And this null hypothesis and alternative hypothesis, this is about gender and promotion opportunities, right? When you say gender and tenure are independent, you're saying we're trying to figure out if males get tenure more often, and if not, then gender and tenure are independently happening for each other. Like we're trying to find about gender equality and promotional opportunities. Is that what this is about?
Yeah, exactly. So we're trying to test, is gender independent of likelihood of getting tenure? Because if it was, we would expect to not see any, significant difference in the, proportion of getting tenure if you're male or female.
Mm-hmm.
And this test is to see if there is some type of dependence of gender based off your tenure.
Okay, great.
Yeah, so even bringing us back to like the ride sharing, is there a significant difference in like the average ride time between men and women? And you would use this type of test to even just say like, hey, these are, there is a difference. But framing it back into like independent versus dependent. So it's all kind of talking about similar things, but I like that you're bringing up like, what is the actual phrases that we're using? And are these variables independent of each other, or is there some type of dependence? And based off of what we found here from the test statistic and the p-value, when we have this here, so our test statistic from this crosstab was 2.206 with a p-value of 0.137. And so our value of alpha which we defined here at a 10% significance level. So let me just, I'm sorry for being a little, this should have been organized a little bit better. So something like just defining that as code to say alpha equals 0.10 because we're at this 10% significance level. And when I say I apologize, I think it would just help to be a little bit more consistent with some of these things because we're using the same exact thing for all of this, for all these different experiments we're running. So I want to stay consistent. So now our value of alpha is 0.1, or we're looking at like 90% of the area under the curve. But our p-value here that we calculated, let's use the same thing. So this value of p is greater than what we would need to be in that tail. So therefore, this value fell within that 90% of values. So we can't say that there is any type of dependence between these two things. So we're saying like gender and tenure are independent of each other, which means that, you know, there's not any types of dependence of gender based on you getting tenure or not. Because
that's a really interesting conclusion, because when you look at just the straight numbers of the chart, there are significantly more men that say, yes, they did get tenure.
Right. But it is also this like proportion difference. So maybe even just in our, you know, when we have in this sample, we have a lot more men compared to women in the total group. So even if we looked at this, let me just reset the index so I can work a little bit more with it. Like if we looked into this proportion, it might actually be somewhat similar. So let's just, if you'll take a little bit of a, so let's just get into no over yes. Where just trying to get like what's the best way to wrangle these things, because that's why I don't love cross tabulation things, because it actually kind of makes it a little harder to work with. Just trying to think like how to, you know, because really all I'm trying to do here is do 50 divided by the total of females. So I'm just going to manually do this, you know, 50 plus 145, because this is really what I'm just trying to get at. You know, so the proportion of, you know, women who do not, or let's do this the other way. Like what's the proportion of, you know, a female who get tenure? And then this is divided by like the total number of, you know, so 74% of women in this group get tenure compared to, let's see, just for men. And I appreciate not too much judgment that I'm just kind of manually putting these in here just for the sake of time and to just show this difference. You know, so 80% of the male population in this sample received tenure. And so this type of test is really just finding like there isn't a significant enough difference between these two proportions for us to say that there is a dependence of getting tenure. Like these two things are not far away from each other enough to say that these values are independent, are dependent.
Mm-hmm. One of the insights, do you think, could be that in the next test that we do, maybe we should run the same amount of men and women so we're able to maybe find some more clear conclusions, perhaps?
So are you suggesting had we had, equal number of male and female here, that maybe we would have seen a different result?
Yes.
Yeah, I think that's interesting to talk through, especially when it comes to like research. There might be more questions as to like, why weren't these groups more equal to each other? And maybe if they were, like, would we expect to see the same type of proportional difference? Or maybe, a question of, kind of poking holes at this experiment, that would definitely be like a valid hole to poke and say, had we sampled for more women, maybe we would start to see more of a significant difference, and maybe our results would be different. So that's why I always emphasize it's important to have like reproducible research, so that, based off what we did here, there's nothing, invalid over what we did. And that's why we're kind of limited in what insight we can draw based off of just what we structured here.
This reminds me of like sampling bias, like who we choose to even sample equals what types of results we get.
Yes, for sure. And I really hope that is a takeaway from our class together, of like, you really shouldn't take anything at face value, because there's a lot of caveats and like considerations that even went into just getting us to this point, of saying things are, not independent. But yeah, you're exactly right. Maybe, we would want to look at like the age difference. Like maybe there's something else going on afoot that is actually driving this type of relationship, where it's really not looking into gender. Maybe, this looks into like beauty. So, there might be other stuff that we should be thinking about here.
Those numbers associated with beauty are hilarious.
Yeah, I have no idea. But this would be an interesting experiment, even to like make like a scatter plot of like, is the higher the beauty, like the likelihood of, some of these tenure, and anyway, yeah. Or like the more students you have, there's lots to experiment with when you have some interesting data. So that's what I am hoping to see in any case study. Folks try to take on, like, if you find this, like, what do you find that's curious about it? And like, what do you want to explore? And I think that type of thing is fun, but teach their own. Okay. So let us go through the last two tests, because next we'll be looking into if things are normally distributed. And this is talking through if, if we can even use the normal distribution for a lot of these things. We talked about the binomial or Poisson in the beginning of the semester, but really haven't touched upon them as much since, because we assume a lot of things are normally distributed, where this test will go to show us if things really are. And we would do it in like a similar way of like, what do we expect to see? What did we actually see based off these expected frequencies? And we would have the same type of test that we've been doing all this time. So just some of the other differences in degrees of freedom. So while you're doing this for homework, I would just say like, have the textbook open next to you just to walk through what exactly needs to go in. So I'm going to breeze through this a little faster, because this is looking into how we would validate some of these claims. So let's say an economist claims that the annual household income is not normally distributed. We would use the same type of null and alternative to structure this. So either the income, these things do follow a normal distribution, which would be our null, or we're trying to find evidence against this to say that the income does not follow a normal distribution, where we need to just specify the mean and standard deviation. So pretty much we're going to use the inputs of what we find based off of a normal distribution. And if our values vary too far from those, then we would have evidence to say this is not a normal distribution. So we state the mean and standard deviation because these are like different statistics we can actually obtain and calculate from our estimate. So this doesn't really tell us the distribution of the data. It won't say, hey, this is actually a Poisson or a hypergeometric. It's really, again, we're like pigeonholing ourselves as this is just saying this is not a normal distribution. So we can calculate this by using the expected frequencies that we'll usually get from different samples. and we would create a mean and standard deviation from these, put it into a categorical format so that we can apply our goodness to fit tests. And we would use these types of sample statistics to create observations of different categories. So these are the ways we would calculate this. Similar, we establish our null and alternative. We would calculate these different inputs based off of whatever information we have available. So we might have a sample that we have with data, and we would take the mean and standard deviation. And based off of that, we can convert the frequency distribution into like a category, and we would multiply by the expected frequency. And in this case, degrees of freedom, we take by the number of, I think by the number of groups we have. Yeah. So we have like the number of intervals we're creating, -1, and then minus the number of parameters that we have at play. And that's why I say like bring up the textbook with you, but pretty much just how many observations do we have -1, and like how many subsets are we making? So in that last example, we just had 2 between, like female, male, but if we had other, splits we were doing like for age, we'd want to account for all the different groupings. And this is all in the same chapter because again, we're using this same exact formula of how we would calculate this. So let me just open up in Python how we would do this for the test of, is this data, does this fit the normal distribution or not? So this is something about income. I just have the data from some type of example test of income. And let me just quickly make like a histogram just so we can see what this looks like. Of values of income. So even just based off of our own understanding, like this kind of looks normally distributed, but we have all these random things going on, and it does seem positively skewed. So, prior to this, we've been treating anything as normally distributed for us to use all of our statistics on it. But now we have the introduction for what does it take for us to actually be able to use this assumption. So based off of these observations of 50 income values, it goes anywhere from, 40 to 250. I would assume this is in thousands. So the average, income is about 50,000, but we see some people making 250,000. So we would calculate the mean and the standard deviation from here for our formula. And this is creating a bunch of intervals for us to create how frequent each value would be given each value here. And let me just unpack this a little bit more. So this is just taking, this is doing some, I want to just unpack this a little bit more so we know what's going on behind the scenes, and it keeps not letting me, because it's pretty much taking each, so I'll just talk through it. It's taking each value in this tuple list and creating bands. So from 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 251. And it is calculating how often does the value of income fall between each interval. So there's lots of ways you could calculate this, even when we learned in some of the earlier chapters. So this is just another way to do it, to create intervals to then test the frequency of like how often does a value fall between 0 to 20, 20 to 40, 40 to 60, and so on. that is all this line of code is doing. So it's saying 6 of these values fall between 0 to 20, 10 of them between 20 to 40, 13, 60 to 80, 10 between, each one of those. So I think I said that a little wrong, but in total, there's 5 intervals, and this is how many values we're taking, the length of how many values actually fall between each interval. So I just talked through what this line of code is doing. You can do this in a lot of other ways as well. And this now gives us the ability to start to calculate a value given the mean and deviation. So if this was a normal distribution, given our value of, given a mean of 63 and standard deviation of 45, what would be the probability of seeing something, a value of 20? It's somewhat probable of, 16%, or maybe let's say, 17% of values would be somewhere, from 0 to 20 here, because this is that area under the curve up until 20,000. So about, let's just say 17% of all observations of income, would fall pretty much right here at 20. So this is just looking into that tail. And we have, our z-score here that can even be used to calculate that same thing that we have here in this cumulative density function. And now we're using the same thing that I had up here of how often would we see, what is the area under the curve that we would expect to see for each interval. And this is creating each of those subsets. So similar to when we were learning for, what's the probability of seeing a value between 2 intervals, this is now seeing each slice of the pie underneath the area under the curve. And that's why I'm multiplying it by -1, just to get us on the positive side. And I'm just going to keep running through this. So now we have the area for all intervals. And now we can multiply that by the total sample size. So this is now getting the expected distribution if this was normally distributed, because we're using our normal distribution types of probabilities. And now using our chi-square test, we can start to see how different is the expected from the observed for the different proportions. So we're starting to see all these different values, and I am just showing it here, but then we will have, you can actually just grab the statistic from these different intervals. So rather than saving it as a variable, this has the statistic there that we can use. So this is just taking the sum of all of those together. And this is just using the formula that we have here and walking through what that would look like. And we have our degrees of freedom. And now we have our test statistic. So we can still use, if we have that alpha, we would want to put that back in there because this would be lower than 0.05 to say at the 5% significance level, we would be able to reject the null hypothesis and say the income of this city does not follow a normal distribution because we see so much, of this kind of positive skew to the right.
I'm a bit unclear about where these numbers are coming from, the 63,000 and the 45,000.
Sure, those values are coming from what we would expect the mean and the standard deviation to be if this was normally distributed. So we just took these values from the experiment we ran and just took the average and the standard deviation. And we use that to create, as if this was normally distributed, what would the area under the curve look like? Because it would be, symmetrical. Given this mean and standard deviation, we're calculating the number of observations that would fall within each part of the area under the curve. But because what we found, given how frequently we would see these values, we see more often all these values that are to the right. This is not very symmetric. So had we seen something symmetrical, given this mean and standard deviation, if this was normal, we should have seen more values that fell on this side of the curve. And that's why we use these values of the mean and standard deviation as statistics to create the normal distribution from. So that's why these values are here. So if this was a normal distribution, we need the mean and standard deviation in order to calculate the spread that we would have expected to see. But meanwhile, we have the spread that we did see. And that spread was not close enough to the spread that we would have seen if this was normally distributed. And it was far away enough where this value of 8.18, because this is the right-tailed test, we're looking to see what that value is. And it is more extreme than this 0.05, which means that we have evidence to reject the null hypothesis.
Okay, 2 questions. So how do we know that those income numbers are in the thousands? I don't know if I missed that in the beginning question.
Yeah,
I mean, obviously income is usually in the thousands, but
I'd hope so.
yeah, that was just me giving my own hunch that we would want to. But again, I think, part of this is me trying to prepare enough context for us to walk through, but also this is all from the textbook. So they probably would have said that, I should have added here in the definition, all values are, thousands. So I didn't explicitly have it written here, but it would have been, had this been from the textbook.
okay. And then also, like when you were looking at this chart here, the histogram, you mentioned the curve and you had your pointer around like the 50 mark. When we're assessing, if it's before the curve or after the curve, are we looking at the mean or the standard deviation to kind of like assess which side it's falling on?
So when you're talking about how did I, because if this was normally distributed, we would start to see like that nice bell curve that we're familiar with. And so that's why I was thinking, like, if the mean was, we have 63.8. So just imagine like a vertical line being here. Had this been normal, we would expect to see most of the values fall here. And then you would have a nice symmetry of values fall on this side and on this side, given the standard deviation of 45. So that's kind of the normal curve we're creating for ourselves. And then we're comparing that against what we actually saw.
Okay, great. So we should use the mean as sort of that midpoint. And then the standard deviation lets us know how much is on both sides of that midpoint.
Exactly. And this is getting back to like just a lot of the fundamentals from this class.
Yeah.
Of like standard deviation says like how spread out are the data points, are the observations. So if standard deviation was smaller, you'd have a very clustered amount of variance, like there wouldn't be a lot of variance. But here, we see standard deviation of 45. So, the average is 63,000, but some folks make a lot more than that. And standard deviation just says like how much variation exists compared to the mean. And it does it in the same unit.
Could we also infer that a lot more people make less than that possibly as well?
Yes, definitely. But that's also what we would have expected had this been normally distributed. You know, we would have seen more on the other side over here. But that's pretty much what we were able to find through this test of, hey, this isn't normally distributed.
Okay.
Any other questions? And that's all, you know, we're kind of really tying the whole course together because a lot of those concepts that we introduced are now being applied and used to like inform our understanding of how things work. And so using like visuals to support that as well. So we're really like exhausting all the tools in our toolkit at this point of the semester. And hopefully, you know, it kind of goes to show like why, you know, why we got here and how we got here. Like the why in the how we got here. It was important to cover all these different steps so that we are now at this level of understanding, which is no
All
small
tying
feat.
together.
Pardon?
It's all tying together.
Exactly. Yeah, like you should definitely feel proud just to kind of understand how these things all work together and be able to apply it because these are really abstract concepts. And so it goes to show you guys have really, you know, we've tackled a lot in this time period. So the last thing we're going to test is this this last one of the Archibera test, which is looking to see if things are normally distributed, just in a little bit of a different way. This is looking more into this kurtosis, or like how skewed is the data. So this is just showing one last way for us to test if things are from the normal distribution. And the textbook covers this as well, because this is more so looking into the skew rather than the normal distribution. So this is just tackling the same type of question, just in a slightly different way. And brings back, you know, one of the first classes sessions we took was like the skewness. So the same null and alternative exist here. So this is now pretty much going to be testing what is the kurtosis. I guess I just have this here because this gets into some other aspects where skew and kurtosis are pretty much trying to measure the same thing, but it's just looking into slightly different ways of measuring that. So feel free to read more on the reference and documentation, but this will be somewhat quick as we just walk through what this would be, because I'm just using the test statistic that we have here, where we would calculate these differences, and being able to, rather than using that mean and standard deviation, just by using the skewness, we would be able to come up with the same conclusion, saying that these do not follow a normal distribution because there's too much skewness in them. So this was pretty short because I just wanted to show, just by looking at this skew that we see, we have another way to show, hey, this data is not normally distributed, because if it was, we would not see so much skew. And this test does that all for us just by putting in the value of income to say that this is not normally distributed. So, and I guess we already have it here at the end to show that positive skew. So we covered a lot today, going everything from the F distribution all the way to how we use this testing framework to start to validate a lot of assumptions that we depend upon from using the normal distribution, and kind of hopefully tying together a lot of the threads of the class into a concrete way for us to start to experiment on the real world that we see. Any questions before we end today's class? I will stop sharing and end the recording.